we're going to continue 8.2. I thought the easiest way was have everything written down. And I can go side by side with Desmos to show you what these graphs are going to be. So we did do an example of how we got a circle, but we needed 1, 2, 3, 4, 5, 6 points to just have a rough idea of what this graph is going to be. Now, I'll show you a quick glance at some of the graphs we're going to be dealing with. Right, you see this one is known as a petal. And you can imagine how many points you would need to try to sketch a graph like this. But let me put that away for now. So this is a graph we did, right? And the idea is to, oh, this actually is a little different. Sorry, it's not, I'm going to erase. Because we did cosine, not sine, sorry. Hopefully that didn't create any confusion. And those are some of the key things that we're going to focus on for doing the graph. Is instead of, you still have this table at your disposal, but the idea is, can I get to my graph without using so many points? As long as I have a rough idea of what my shape is going to be, just by looking at the equation, that should help a lot, right? Like, you have an idea of when a graph is a parabola or an absolute value or a square root. And that's what I'm trying to get to, is how can we look at the equation so that we know roughly what the graph should be. So right away, this clearly was a circle. And that's how there's going to be a few different ways to write circles. So one is having r equal cosine all on its own. Key thing is the argument for cosine has to have a leading coefficient of 1. So you don't want any numbers inside that argument. And also r equals a sine theta is another example. Now the only thing that varies between sine and cosine is you have the circle that's, its diameter is right on the x-axis, versus sine has its diameter on the y-axis. And of course, when you have a positive a, your circle for cosine is on the positive side of the x values. When that coefficient for cosine, not the argument needs to be 1, but the coefficient for cosine is negative, it's on the negative side of the x value. And similarly, sine works the same way. If it's positive, it's going to be above. If it's negative, it's going to be below. And I have an example here where I have a negative sign, and I'm going to show you how it resembles this graph here. If you notice, I'm going to zoom in a little bit, and a key thing to recognize is how that -5, the negative tells me on what side of the graph it's going to be, and the 5 tells me how low the graph is going. Even though it's a -5, it goes to the -5 on the y value. Whereas for the cosine, right, that showed us, since it was a 3, we know how far that went on the x-axis to +3. So those are little things, right, we can start picking. So positive is on the positive side of the x, negative is on the negative side of the x. And that a lot of these graphs have that same behavior, where the positive and negative sine or cosine either being on the left or right of the y-axis or being above and below the x-axis. And another circle is just r being equal to a constant. That just makes a circle that's centered at the origin. So any circle you can imagine, I can do one really quickly. R equals 4. It's just going to make a circle centered at the origin with a radius of 4. That one's pretty straightforward. Now, the next 3 have this general look where there is this obviously sine and cosine function, and then there's this constant term adding, and then sine and cosine both have these coefficients, and then there's this constant term. Now, depending on what's going on between these values, that constant term and that coefficient is going to dictate if it's either a cardioid, and some people call a heart. I like to call one a dimple, and then there's one that's a loop. Right, so let me try to zoom out. It's going to be these 3 cases here. Hopefully you can see that. So one looks like a heart. One has this little dimple, almost like an apple. And then one has this internal loop inside of that rotation, that circular shape. Now, how do I know which one is which? So to start, looking at this cardioid, the main thing that you're going to notice is that coefficient and constant term are the exact same value. Now, sure, there can be a negative for this coefficient, but that just speaks to what side the cardioid is pointing towards. And it's the same as what we did in our circles. If you notice, if I have positive, if there's a positive between that constant term and the trig function, that cardioid or that heart, it looks like it's pointing in that positive direction. But it still does have this this sort of curve heart shape. If it's negative, it points in the downward direction. And for cosine, same concept. If it's positive, points out in the positive direction. If it's negative, it points in the negative direction. So I have a couple examples to show you. Let me get rid of this circle. So I have 2 examples here. So I have one for cosine and sine. So this first one is one of cosine. And if you notice, so it says 2 minus 2 cosine theta. So we have these 2 are the same. So I know it's going to be a cardioid. And the cosine one, since there's a negative, I know it's going to point in that negative direction. Now the sum of these 2 numbers shows me how far I go in that direction. And you're going to see right now. If you notice, like it's doing what I said, it's pointing in that negative direction, and look how far in that negative direction it goes. If you look here, you see, I'm going to zoom in, right here is a -4. So that's a way to dictate how far that's going, because like I said, you're always going to have the table at your disposal. So if I want to verify, well, I'm not sure if it is pointing in that negative direction. Well, you can always make your r theta table. And I know this direction is pi. I can plug in pi and find my value for r. And that should give me the furthest edge of this cardioid. That's why the table is still very useful, because it's going to still show me, I'm going to be able to have a rough idea of what it looks like, and my table is going to correspond to it. So I'll know that I'm on the right track. And then here's a second example down here. I'll point to it, where now we're dealing with sine. Now, if you notice, again, that constant term, that coefficient are equal. Hence, we're going to have a cardioid that either points up or down. And since it's positive, I know it's going to point up. And I can add those two numbers together, and I know that's going to get me to this high point, which 4 plus 4 gives me 8. So this should be exactly what we said. It's pointing up, and if you notice, right at that tip, it gets exactly to 8. I'm going to point to it, and that's how high it goes. Now, the next two, again, have that same overall shape. And I like doing these side by side. One has like this dimple. So if you notice, it doesn't actually touch that origin like the cardioid does. Now the loop does touch that origin, but it clearly has this loop inside. Now, how can I tell the difference? Well, for one, that constant term and that coefficient are not going to be the same value. So for the cardioid, the moment these two numbers are the same value, you know you have a cardioid. The moment that they're not the same number, you know that you're either dealing with this like apple/dimple and a loop. Now, how do I tell the differences between them? You can choose to memorize that when the constant term is bigger, and when I mean bigger, I'm just talking about the overall number. I'm not necessarily talking about if one is negative or positive. It just has to do with the A, B itself, like if you're doing the absolute value of each. So when this number is larger, you have this dimple one. When the coefficient is larger, you have this loop. But just like I said a second ago, even if you don't know which one it is, one thing you can clearly notice is to have the dimple, these 2 points are on opposite side of an axis. Now again, this is the sine version because it's specifically this would be a sine with a negative because it's pointing in the negative direction. The positive one would look like this with a dimple, but either way, the dimple has these 2 points on opposite side of an axis. For cosine, the dimple will obviously point either in the positive x direction or it's going to point in the negative x direction. But still, these 2 points are on opposite side of an axis. Where the loop, the 2 points kind of indicating the direction are on the same side of an axis. So that's something to remember. So opposite, same. Or if you want to just remember when the constant term is larger or when the constant term is smaller, right? And the negative and positive just tell us on what side of the axis we are. Cosine pertains to the x-axis, sine pertains to the y. So luckily everything still coincides with what we've learned before. And I put a plus b and a minus b because just like the cardioid, when I added these two numbers together, it gave me that point that it was how far the point of that direction is what I meant to say. And same thing. So these points are determined by doing the sum of that constant and coefficient, and then taking their difference gives you those smaller distances from your main axis. And I have a couple examples of those. So if you notice, so right here I have a sine one and a cosine one. Now, if you notice, in this first example, again, you can either memorize, oh, the constant term is larger, so I know I'm going to be dealing with a dimple. It's sine, and that coefficient is positive, so I know it's going to be pointing towards the positive y-axis. And then I did say you can add and subtract. So 3 plus 2 gives me 5. That's the furthest it's going to reach. But 3 minus 2 is 1. That's how close it's going to get to the other axis. So let me show you. So here it is. And I'm going to go closer so you can see how, if you look here up top, that's 5. If you look here at the bottom, that's 1. Because 3 plus 2 gives me 5. 3 minus 2 gives me 1. And that's how you can see the dimple is pointing in the positive x direction. But again, the goal I want you to get to is remembering the format. That there's a cardioid, there's a dimple, and a loop. And how can you determine them? Well, the cardioid's clear. The constant and the coefficient are the same. The dimple and loop, the constant and the coefficient are different. But I can always use my table to help me decipher which one it's going to be in case I forgot about one being larger and smaller versus the other. And then here's the next example. It's a cosine, so I know it's going to either be pointing in the positive or negative direction. And since the coefficient is negative, I know it should be pointing in the negative direction. And because the constant term now is actually smaller, I know I'm going to be dealing with the loop. And here it is. And you can see we have, and of course, adding 3 plus 5 gives me that 8. So it goes to negative 8. And then, but 5 minus 3 does give me 2. And if you notice, that loop does give you a negative 2. And it is pointing, because it was a negative 5, or the cosine was negative, it points in the negative direction. Again, I know for some of these, I showed the positive, the negative, positive, negative. I don't want to get too much information that you're going to forget. So I'm trying to consolidate it as much as possible. And lastly, there are that example that I showed you at the beginning dealing with these petals. Now, these have a slightly different format. They actually almost look like circles. The only difference is they have a coefficient in the argument. Both of them do. Now, like I said, I'm trying to keep things simple. So once it has a coefficient, that coefficient either makes the circle, those petals, larger or smaller. But two key things that are going to really help you get to this graph is when that coefficient is even, you're going to have double the number of petals. So if you have a number of 2, you'll see 4 petals. If you have 4, you'll see 8 petals. If you have 6, you'll see 12 petals. But when it's odd, you have the same number of petals. So if it's 3 coefficient for theta, then 3 petals. If it's 5, you have 5 petals. And lastly, these always look symmetric. So when you're sketching your graph and you have one side, you can use the idea of symmetry to sketch the opposite side. So looking at this example here, it's sine. The 3, I know that's just how large, sort of the tips, I would say. The tips of the petals, it would be given by that A. So, and the nice thing about that is if you are using a table to start you off, if you were to get an answer for 3, let's say for this r equals 3 sine 2 theta, if you were to get a 3, you know you're exactly at the tip of a petal. And that can help you then sketch it knowing this symmetry concept of them. And because it's a 2 in that coefficient for theta, I know there should be 4 petals. And let's look. So if you notice here, there's clearly 4 petals. It's hard to see that the petal goes as far as 3, let's say at the like pi over 4 direction. But it does. It really does go as far as 3. And actually, I think there's a way for me to show you by making a circle that has a radius of 3. So if you see, I made a circle with a radius of 3, and that intersects perfectly at the tip of each one of these petals. So the nice thing about that number, it does tell us how large these petals are getting. And this last example, 4, so the tips of the petals are going to be as long as 4, and because it's 5, I don't get double the number of petals. I have the same number of petals, which is 5. And that's the example I started this video with. And again, look how there is symmetry to this graph. Now, the symmetry is not on the y-axis. The symmetry is on the x-axis. And that's where things can vary. In the previous example, we had symmetry over the y and the x. So keep that in mind. Again, if you want to add more additional concepts of symmetry, you can, right? I can change one of these numbers, 3, right? Because it's sine. You might want to say that there'll definitely always be symmetry over the y-axis, right? Look, odd number, you can see the odd petals. Even number, double number of petals. So that's one thing. Again, I don't want to add too much information, but something you can always rely on is for cosine, there will always be some type of symmetry on the x-axis. For sine, there will always be some type of symmetry on the y. Sometimes, for when you have even number of petals, you have symmetry on both the x and y axis. Now, play around with some of these. Go on Desmos and really look at these formats and try to see how these graphs look. Make them larger, make them smaller, put a negative. Again, these are just a few descriptions, and I try to keep it as basic as possible that can help you memorize. Because on the exam, I will have you sketch one from scratch. But a way for me to ask multiple versions of this question, I will have you just pair or match the equation to the graph. I'll make another video with a couple examples of these petals, but I don't want to get this video to be super long. So I kind of just wanted a video of just the descriptions. And I'll make a second video with some examples. Thank you.